All right, hey folks, continuing on with chapter 8. Love me some flaming lips. All right. So, learning goals. Okay, so we've gone through drawing Lewis structures for covalent and polar covalent compounds. Okay. So what we're going to continue along with here, oops, let me get my highlighter. What I'm going to continue along with here, assuming that I know what I'm doing on my computer. Okay. So we've started getting into the Lewis structures of covalent and polar covalent, obeying the octet rule. And in that last lecture, we looked at Clark's rule to do double bonds and triple bonds, but we haven't looked at deficient valency or expanded valency yet, okay? So that's what I'm gonna pick up with from here. So that's learning goal 5. Also in this video, I think we should have time to do learning goals 6, 7, and 8 as well to wrap up the remaining things of Lewis structure. But I'm keeping my eye on the time, and let's see how we go, okay? So exceptions to the octet rule, because of course there are, because chemistry is the science of exceptions. So the second row elements, carbon, nitrogen, oxygen, fluorine, always obey the octet rule, right? So down here, carbon, nitrogen, oxygen, fluorine, they always obey the octet rule. However, boron and beryllium often have fewer than 8 electrons, okay? So they are, that's what's called deficient in their valency. So they have less than the octet rule, okay? And that's because they're small, right? These, we remember from our periodic trends, that boron, beryllium, lithium, these are very small atoms, okay? So they can often take fewer than 8 and be okay with that. But the main thing is the second row elements never exceed the octet rule. They just don't have enough space to do it. They're not big enough, okay? However, the third row elements, so now starting with sodium, magnesium, aluminum, silicon, etc., and below, so third row and below, they often satisfy the octet rule. However, they can exceed the octet rule because with that level 3, okay, 3D is possible. So they can spill into the d orbitals. And because they can spill into the d orbitals, they can exceed the octet rule. So we call this an expanded valency. And on the other lecture, I called that Texas-sized valency because everything is big in Texas. So when writing the Lewis structure, okay, try to satisfy the octet rule first. And if there are extra electrons remaining, they can be placed into atoms having d block electrons. So things at level 3 and higher. Of course, Clark's rule will also help us predict that. And we're going to see this next. Okay. So draw Lewis structures for the following molecules. All right. So I'm going to play some music in the background. And I'm just going to keep going like I've been doing. I'm going to first sum up the valence electrons. Then I'm going to do Clark's rule. And then after I see Clark's rule, I'm going to make my decision on if I need extra electrons, like in the form of a double bond, or perhaps I need an expanded valency, or perhaps I need a deficient valency. Okay? So let's do it. Let's bring back the flaming lips here. Okay, here we go. PCl5. So phosphorus. 1, 2, 3, 4, 5. And chlorine, 7 times 5. Okay. So now Clark's rule. 6 atoms, 6 non-hydrogen atoms, right? Plus 2 equals 38. If X is less than the number of valence electrons, expanded valency. And we can see that because this is a phosphorus with 5 chlorines, right? So phosphorus has the higher bonding capacity, okay? And I've got 5 chlorines to put around this thing. So my phosphorus is Texas-sized, right? It can take 10. It has 10 electrons. But let's count them up. 2, 4, 6, 8, 10 out of my 40, okay? And now I'm going to use the remaining electrons to satisfy the octet rule, okay? So now that's 2, 4, 6, 8 per chlorine, right? 8, 16, 24, 32, 40. Brilliant. That's it, okay? BF3. 1, 2, 3 for boron. 7 for fluorine, and there's 3 of them to give me 24 valence electrons. Okay. What about Clark's rule? 6 times 4 plus 2 gives me 26. So, do I expect double bonds? Maybe from Clark's rule, okay? However, boron is an exception. Boron often just takes 3 bonds or 6 electrons, okay? I have to turn this music off. I'm so distracted. I hope I haven't distracted you with it. I was having fun. Now I've got to focus. Okay, so as I said, boron often takes 3 or 6 electrons. Boron and beryllium both. Okay, so this is where Clark's rule might confuse you a little bit. So watch out for those boron and beryllium exceptions. And now I'm going to fill in the rest of my electrons. Okay. 2, 4, 6, 8, 16, 24. Great. Okay, so I'll circle these. Okay, so that's it. Okay, SF6, we did this one already, if you recall. I think we did this one already. But let's do it again. So sulfur is 1, 2, 3, 4, 5, 6 plus each fluorine. And there's 6 of those, and each fluorine has 7. So that gives me 48 electrons I have to use around. And now with my Clark's rule, 6 times 7 plus 2, that gives me 44. So the fact that that's different by 4 tells me that SF6 has, or that sulfur has 4 more electrons than the octet rule, so 12 in total. So let's see how that works out. Okay, so you can tell just from the formula, hopefully you can tell from the formula, that it seems reasonable that it's going to be a sulfur surrounded by 6 fluorines, right? So 8 is the norm, but look, now sulfur has 2, 4, 6, 8, 10, 12. So that's how I got to that number 12, because the difference between that of 4 less, tells me there should be an expanded valency for sulfur by 4, okay? And so now we've got to use up all 48 of our electrons, and hopefully you can tell by now the way this is going to go. We're going to just fill up the octet rule for all these fluorines. And I'm not going to count up to 48, but if we were to count them, that's right. We would arrive at 48. Okay, so that's SF6. Okay, so this one's interesting. ICl minus. Okay, so iodine has 7 valence electrons. Each chlorine has 7, and there's 4 of them, plus 1 extra electron because of the minus charge, right? And so that gives me 7 times 4 is 28. So that gives me 36 valence electrons that I've got to spread around. So there's 5 non-hydrogen atoms. 6 times 5 plus 2 gives me 32. Okay, so now this one's interesting because you can see it's also less by 4, just like this one. Okay, and if I start spreading around these bonds, you notice that I've only got 4 chlorines. So how is it that I'm going to get 12 electrons around the iodide? Well, let's just wait on that, and let's finish the lone pairs for chlorine. And let's see how many we have remaining. Okay, so we need to use 36, right? So we've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So I have 4 left. Where are they going to go? 33, 34, 35, 36. They're going to go on the iodine. And that's why this has an expanded valency, right? Because we noted that 8 should be the norm, but when there's a difference of 4, that means really iodine is going to have 12. And here it is, 2, 4, 6, 8, 10, 12. Okay? And because this is an ion, we put brackets around it and put the minus charge. And there's our Lewis structure for ICl4 minus. Okay, beautiful. So I'm going to move on to the next topic here. Okay,